nickel oxide photoelectrode, the dye-modified nickel photoelectrode, and finally the hybrid photoelectrode, which is composed by these dye-modified nickel photoelectrode, absorbing nickel palladium nanoparticles. So the final electrode was the hybrid one. So we checked the activity against CO2 photoreduction of all these electrodes. And we start with the nickel electrode. As you can see, the nickel electrode is not really active when under light and in dark. The same current is measured for this electrode in both cases. For a solution of Na2SO4 saturated with CO2, degazed from oxygen and saturated with CO2. As you can see, there is no difference. Next slide, please. So when you take the nickel electrode modified by the dye, I mean, where you absorb the dye, also there is not a significant difference in between both states, with or without light, under dark and under light. So there is a very, very little difference. Next slide, please. Finally, we take the hybrid photoelectrode where we absorb the palladium nanoparticles on the dye-modified nickel oxide electrode, and we check it if there is CO2 photoreduction. And then we can see a little effect which started earlier and goes when the black one is the solid line is under dark, and the dash line is under light. As you can see, there is a little difference, but we check it. Next slide, please. We checked the same electrode by linear sweep photovoltammetry, and as you can see, this is under dark. When you use the same electrode in the same solution, which is saturated with CO2, under dark there is very, very little, which is not really significant. Whereas when you light, you put under light, there is a very important effect for CO2 reduction, which start as soon as 0.6, but not very, very important. But you can see that it starts earlier. That means that there is a really synergetic effect in between the nickel oxide, the dye, and the nanoparticle of palladium. So next slide, please. And we check it again by twice the nanoparticle amount adsorbed on the electrode surface of nickel oxide modified by the dye. And then we get more effect on CO2 photoreduction. And this means that when you improve, when you you enhance palladium nanoparticle amount on the electrode surface, then you get much more higher current on the electrode. And this current is only due to the CO2 photoreduction, of course, and we checked this. So next slide, please. So this is another larger, on a large potential range for the three electrodes: nickel oxide modified by the dye, nickel oxide modified by the dye with one amount of nanoparticle, and twice the amount of nanoparticle of palladium. And then you can see here the effect is also can be seen, but the most important is here. As you can see, when when you have the nickel oxide with the dye, there is not really a great effect. But when you put the palladium, you have an increase of the current, which start as early as -0.4 or -0.2 or 0.4. But it starts before, as I told you, it starts here, but you can see it better here. And when you enhance the amount of palladium, as you can see, there is this wave which appears clearly. This is the proof of concept that we have a real effect of the dye on the palladium. When the dye is negatively charged, the palladium can get photo reduction of CO2 easily, and it starts really much more earlier. This is the photoelectrode we did, and we think that this photoelectrode can be used as so in several reaction of as you call CO2 reduction reaction, and by sunlight. Next slide, please. Hello? Yeah. I can conclude that because there are some information I didn't give in the talk, that I can ask, if you ask question, I can answer. An example of proof of principle for simple three-component photoelectrode active towards CO2 reduction conversion by sunlight-driven photoelectrochemical catalysis of CO2. This type of photoelectrode bridges the gap between two classes of photoelectrode. The first is the heterogeneized molecular component, which contain organic dye and nickel semiconductor. This is known. We did show it before since 2012. And what we did is this composite nanomaterial, where we combine between organic, inorganic material, and we make it layer by layer. The suitable matching of the energy level of the components results in a good recorded catalytic activity. And the CO2 reduction conversion depends on the nanoparticle of palladium catalyst, which is necessary to channel and to store the electron away from nickel dye surface and to avoid accumulation of reduced dye at the electrode surface. The palladium really avoid it. We measure significant quantities of CO adsorbates, and we detect them by anodic stripping voltammetry, such as CO2, formic acid, methanol, ethanol, and the quantification and mechanism are under study. The dye is really necessary to photoactivate the semiconductor nickel oxide, and also it improves the stability and the catalytic activity of the photocathode in a super synergetic manner, as the CO2 photoelectrocatalysis occur at in between 0 and -0.3 volt versus RHE, whereas for CO2 electrocatalysis with palladium, only palladium, it occurs at -0.6 volt versus RHE. Thank you very much for your attention, and I would like to thank you again for your kind invitation to present this small work in our group. Thank you very much.
Thank you, Professor Juni, for your nice presentation, and you have completed before time. Thank you very much. Now it is open for question answer session to the audience. Any question from the audience?
I hope the principle was not that much difficult to understand for physicists. I know that the major part of your group are physicists. Okay.
Bani? Hello?
I hear you. Yeah. Can we use visible light for this material for photocatalysis? It is. This material is is suitable for visible light catalysis of CO2. It is really used for visible light catalysis of CO2 because the dye, the observers of the dye is in visible range, and the dye is the la force motrice, the power to enhance, to track the mechanism of CO2 reduction reaction. Is it? Hello to unmute. I'm sorry, I didn't.
There is another question from Archana Tiwari.
Yeah, palladium. Okay. Yeah, we use it palladium because we started. This was a first work on this kind of electrode, and it was just a proof of concept in a way. We can use any catalyst, but the only problem is to get these energy levels, as I show you in my slides, because the dye has to transfer the electron to the catalyst. So you have to match in between the catalyst and the energy level of the negative dye. And this is not really very difficult because the energy level of the negative dye is high to transfer the electron to the catalyst. We did it because there was a work. I didn't find the reference. I'm sorry, because I was a little bit ill. Because there was a work before on a catalyst which was an enzyme, or an enzyme, organic enzyme, but the enzyme was very quickly empoisoned. So that's why we take palladium instead of an organic enzyme, and it works better than this organic enzyme, and it was not poisoned in this case. No, nickel oxide is not nickel oxide is not used as nanoparticles. It is used as layer, blocking layer, and we take nickel oxide as powder and we makes it a mesoporous layer, but not mandatory nanoparticle. It has to be a powder, and we must make this layer of mesoporous nickel oxide as porous as possible.
So any other questions from the audience?
For unmount, I don't know. Is the process is similar to PUC water splitting? It is similar, but we avoid water. We didn't want to split water. But I think you can use the same principle to split water. Okay, you are right. And I think you can also use this kind of photoelectrode combined with another photoelectrode on the other side. This is cathodic, but you can use anodic one in the other side, and again, and you get the full solar system to split water and to reduce and oxide, reducing in one side and oxidizing in the other side. It is, I think it's possible. We didn't do it, but we think to do it.
Hi, sir. Good afternoon.
Good afternoon.
Sir, this is Vani.
Sorry?
This is Vani.
Yeah, I hear you.
Yeah, yes, sir. Sir, in this system, in this photochemical cycle, how could enter that carbon dioxide into that cycle? Because in a natural process, CO2, it's in air. It will take by the plant, and along with water, it will split the water, and the oxygen will be released. It will be entered into the PS2 system. So this is a common process. See, in your this one,
CO2 is absorbed on palladium, is first hydrated and then absorbed on palladium. It may be in form of HCO2 minus. This is the first reduction process. Maybe there is a proton transfer to CO2. We didn't check really the mechanism, but it works, really works. And we get methanol. So we think that the first step is the hydration of CO2 and then electron transfer from palladium to CO2. We think also that palladium started first by absorbing, in a way, activation and absorption of CO2, but not that much, because there is no poisoning of palladium, and we hope we can check the mechanism better than this in the future. I'm sorry to don't give a convincing answer, but that what we know that byproducts, as I told you, are methanol, CO, and other byproducts. So the mechanism is probably there is a protonation of CO2 and then electron transfer, something like that.
yes, thank you, sir. Sir,
I'm
one
sorry.
more. Yeah,
I'm sorry.
Yeah,
Sorry?
it's okay. Sir, sir, one more clarification, sir. Sir, is there any research you conducted if the I mean sunlight captured by the dye that is
Yes,
compared
the
to that is
sunlight, the
that is
sunlight
compared
harvesting
to yeah,
is
yeah,
done by
yes,
the dye. Yeah.
yeah, it's absorbed by dye. It is
Yeah.
any comparison you done with any I mean natural chlorophyll content in the plant, because that's
Yes,
the common
yes.
process. Yeah.
Yes, the dye is this dye is very common. It's a commercial dye. You can use other dyes, but the problem is that we tried to do it in cathode, photocathode. But if you want to do it in photoanode, you can use also titania with another dye, another N type dye. And then you can oxidize instead of reducing. You understand?
Yes. So my question is, if any comparison you done with the natural process, like the plant leaf having
No,
chlorophyll
we
content.
didn't. No, we didn't try to check with natural products. No, but I think it's very interesting to try to check with this kind of dyes. There are many organic natural dyes that you can use in this case. Okay.
Correct.
Yeah,
Correct.
you're right.
Yeah, yeah.
No.
Thank you, sir. Thank you very
Sorry.
much.
Yeah.
Perfect.
Sorry.
There is another question you can see in the screen.
The similar to PUC water splitting, I think I did give an answer for Murali Manoj. Yeah, I couldn't. What is the other question? I didn't see it.
Yeah, there's the question from Murali Manoj.
Yeah, I did. I told you that it is similar to water splitting. It's similar to photoelectrochemical catalysis of water, and it is similar, but it depends. We use it. We didn't want to split water, and as I told you, we avoid water because of palladium. We think that palladium and water doesn't work well, doesn't combine well. That's why. But hydration in our case is important, and there is also protonation of CO2. So I really don't know the mechanism. We suppose there is a sort of mechanism where hydration occurs of CO2, but we don't really know. But it is a similar process like PUC, photoelectrochemical water splitting. It is similar, of course. I think we can use the same the same process, the same photoelectrodes for water splitting, but not mandatory palladium, something else maybe.
Okay. Professor Juani, this is the last question from my side. Actually, this is just I want to know. You have used palladium for this, surface modification of this disensitized nickel oxide photocathode, right?
Yeah.
And what about the size of this palladium nanoparticles? Have you seen the size?
Yeah,
Size of
what
this
is
palladium
what
nanoparticles?
we check it. I have some. I don't know how to show you because I'm not
Yeah,
accustomed,
yeah.
as I
So,
told you. But we check it about the electrode before
mhm,
and after CO2 reduction, and the
okay.
modification is really not
No,
important
my
at all.
my question. See, suppose I will change this nanoparticle size, palladium nanoparticle size. So what is the effect on this reduction of carbon dioxide? So you have tested with a particular size of these nanoparticles, right? Palladium nanoparticles.
Uh, uh, as I told you, the palladium nanoparticle is not mandatory. You understand
Not
me?
mandatory.
It's not mandatory. You can use, as I
Not
told you,
mandatory.
before our, there is another work in the same case where they use it
Mhm.
instead of palladium nanoparticle as catalyst, they use it organic enzyme.
Okay.
Supported organic enzyme, and that was also success. But the problem in that case is the poisoning of the enzyme. That's all, because there is a turnover for the enzyme and it's going to stop. Palladium is we take it as catalyst, but we can change it. We can use another catalyst. It was only for proof of concept.
Yeah. Okay. Thank you very much, Professor Giovanni, for your nice
Thank
presentation.
you very much.
And
I hope I can join you later
yeah,
because
yeah.
I have to go to the doctor. I'm
Yeah.
sorry. I have to
So
go
thank
to.
you very much again, Professor Giovanni, for your nice presentation.
Thank you
And
again for your invitation. Thank you very much.
yeah, thank
Yeah,
you.
nice to get you.
Dr. Ove, can you start this second presentation?
Yes, actually, we are waiting for the speaker to join.
Okay.
Yes, just give a minute. Professor Burman?
Yes.
Yes, hi.
Can you?
Yes, Professor Tripathi?
Yeah. So we will start this second talk.
Okay, I cannot switch
Yeah.
on my video for some reason.
Okay, let me just introduce the second speaker to the audience. The second speaker is Professor Anjan Barman. He is from SN Bose National Center for Basic Science, Kolkata. And his talk will be about ultra-fast spin dynamics in nanoscale engineered ferromagnetic structures. Professor Barman has research interest in magnetic thin films, nanostructure, multilayers, and heterostructures. Also, he has interest in ultra spin or ultra fast spin carrier and phonon dynamics, besides others. He has been awarded various awards and fellowship. To mention a few, he has been elected as Fellow of Institute of Physics, IOP UK in 2021, and Fellow of Indian Academy of Science, Bangalore in 2020. He has been a UKRI Research Award. He got UKRI Research Award Fellowship from 2018 and 2012, and also a JSPS Fellows in 2003. With this brief introduction to Professor Barman, let us invite Professor Barman for his talk. Professor Barman.
Okay, can you see my screen?
Yeah. Talk is for 40 minutes and 5 minutes for question and answer.
Sure. Okay, so thank you. So I hope my screen is visible and I'm audible. So
yeah, audible, fine.
Yeah, okay.
Perfect.
Thank you for the kind introduction. And I'll start by giving a very brief introduction of the research activities in my group. We work on various pillars of spintronics and magnonics. We work on ultrafast demagnetization, magnonics. We work on pure spin current and relative phenomena. We work on various kinds of interfacial phenomena and topological magnetic objects. We work on different new material like Hester alloy, 2D materials, topological materials, and also quantum magnonics and so on. We have indigenously built different techniques like time-resolved magneto-optical Kerr effect microscope, optical pump probe microscopy and spectroscopy, broadband and spin torque ferromagnetic resonance, below light scattering spectroscopy. All of these are unique in India, and we will show use of some of those techniques to study novel phenomena in ferromagnetic nanostructures, thin films, and heterostructures today. So the world of spintronics, as you all know, has shifted from the conventional giant magnetoresistance, GMR, and sort of the granular magnetic media. And right now, the focus is much more on spin orbit torque and spin transfer torque related magnetic random access memory, as well as various kind of magnonic properties and devices, voltage controlled magnetic devices, atomic spin based logics, various topological phenomena like Skyrmion Hall effect, and so on. On the other hand, a new topic called magnonics, or which actually deals with the propagating and localized spin waves in a magnetic system, where the spins do not propagate or travel themselves, but they actually process, and the phase of the spin wave propagates through the media in 1, 2, and 3 dimension. They are used through periodically modulated magnetic media that opens up magnonic band structures and band gaps. And you can see novel devices like holographic memory, magnon transistor, logic, and other devices based on this. So magnetization dynamics is at the core of this phenomena. And you can see some of this phenomena, and this is the time scale. And you can see the time scale ranges from a femtosecond, that is 10 to the power minus 15 second, which is an extreme time scale, to microsecond and millisecond, which is sort of much slower. And the fundamental exchange interaction and spin orbit coupling, they fall in the femtosecond time scale. And here, laser induced ultrafast demagnetization and spin transfer and spin orbit torque, they fall. Then magnetization precession and damping, they fall in this picosecond to nanosecond time scale, where magnetic writing, vortex core switching, and spin wave that takes place. And the slower dynamics is the domain wall dynamics, which is actually the core of present data storage technology, which falls in the microsecond to millisecond time scale. So the ultra-fast demagnetization is the fastest phenomena which occurs in the femtosecond or 10 to the minus 15 second. And you can see the first work on this was done or reported in 1996 when Borpier et al. Showed that a magnetic material or nickel can be partially or fully demagnetized in presence of a magnetic field by shining with a laser light, and that laser is a femtosecond laser, and then it follows a recovery. And they use the phenomenological three temperature model consisting of three different electron bath, like the electron, lattice, and spin bath, which couple with each other and interact. And so till then, it has gained a lot of momentum, and there have been many, theories which try to explain this. And one of those is basically the spin flip scattering process. Depending on different kinds of, depending on the media, it can be different kind of spin flip process. And then there can also be transport process or spin transport process, which is a super diffusive spin transport or laser excited hot electron plays a crucial role through spin dependent transport or thermal current, which can also cause this ultra fast demagnetization. And here the temperature changes. So we already told you that three different bath has different temperature. So you can see the electron temperature, spin temperature, and lattice temperature, and how they evolve in time. Lattice temperature being the slowest one, and it catches after some time. So actually the physical heating of the system occurs in picosecond time scale, whereas the non-thermal process like electron and spin that occurs in much faster time scale. And this is the super diffusive spin transport, which shows that the electron become mobile at because they are shifted from the D band to the SP band, where the mobility is faster, and they travel at two different velocities for the upspin and downspin, and that causes these ultra fast demagnetization through spin transport process. That was proposed by this paper in 2010. So the precessional magnetization dynamics is a slower one, where the spin angular momentum precesses around an effective magnetic field with a damping. So you have this equation where this is the precessional torque and this is the damping torque, and this effective magnetic field consists of a large number of fields in the system, which is both space and time dependent, and that causes the system to be very complex. And the simplest way to describe it is to propose a plane wave solution to that, where the magnetization can be shown by a plane wave, and under the uniform precessional condition, it can be expressed by the so-called Kittel formula. And on top of that, you can also write this is basically the precessional dynamics. We can see the precessional oscillation on top of this background. And if you remove the background, you see this time resolved precession, or this beautiful oscillation of the spin. And you can describe it by this harmonic function with a damping. And the damping, or the Gilbert damping, can be extracted by using this expression, where tau is the relaxation time of the precessional amplitude. So we measure it by using the time resolved magneto-optical Kerr effect in our lab, which is an optical technique based on a femtosecond laser and a optical palm probe technique. We take a femtosecond laser and split it into two parts. The strong part goes through a second harmonic generator and produces, so this is the red light, and it produces a blue light, and that is passed through a fixed time delay through various optics onto the sample, whereas the probe beam is passed through a variable delay generator, and then so that causes an optical delay between the pump and the probe beam, and then it is recombined with the pump beam and collinearly focused on the sample, so that we can actually measure the focused or the spatially and temporally resolved time resolved magnetization dynamics from the system with a spatial resolution of about 1 micrometer and a temporal resolution of 100 femtosecond. This is another setup which is based on a femtosecond amplifier system, which is Libra in this case. And here also we do this 2-color pump probe experiment, but here we do not do the collinear measurement. It's a non-collinear measurement. And here pump and probe are not tightly focused, but here the spatial resolution is only 200 micrometer. That's not a problem because we do measure with a better time resolution of 40 femtosecond and a pump wavelength variation from 250 to 2200 nanometer, which gives us the time resolved spectroscopy as well. So these are the photographs of some part of this lab. This is the time resolved microscope, and this is the optical pump probe technique. So this is the Libra system, Topaz second harmonic generator, and this is the close to the sample and how pump and probe fall on the sample, the magnetic field, the detection, and so on. So here the time resolution and the spectroscopic study are given. So we start by a simple problem, and before doing that, we try to motivate ourselves by saying that we already said that there are various mechanisms which govern the ultrafast demagnetization, and one of them is spin flip scattering process, and another is thermal transport or spin transport, which is a non-spin flip scattering process. Our goal is to understand whether these two processes can coexist in the same system, and if so, can we control them together? So for that, we took a system called a cobalt palladium multilayer, which shows a perpendicular magnetic anisotropy. Here, thickness of the cobalt is 2.8 angstrom, whereas palladium is 9 angstrom, and we repeat the bilayer, cobalt palladium bilayer, from 2 to 125. So as a result, the perpendicular anisotropy changes from the hysteresis loop. You can see it deviates from the square loop. As well, there is a variation in the overall thickness of the sample. So this is the time resolved dynamics. So here you can see the negative delay, the zero delay, the ultrafast demagnetization, relaxation, and the damped precessional dynamics in the system. These also show a terahertz emission at about 3 terahertz after the demagnetization, which shows that terahertz emission can have a role in the demagnetization as well. So this is the phenomenological 3-temperature model, like I said. So these are 3 coupled rate equation with the electron lattice and the spin temperatures and their coupling constant. They can give rise to an expression for the ultrafast demagnetization of the system, which is given like that. Here tau m is the ultrafast demagnetization time, tau e is the relaxation time, and we try to understand what happens as we vary the number of bilayer repeats from 2 to 125. So this is the data, and you can see that for n equals to 2, and the down arrow shows that the fluence increases along this direction. So as the fluence increases, the overall quenching increases, but it remains as a one-step demagnetization or the type 1 demagnetization. And as n increases, this remains the same, but as we go to n equals to 50, instead of a single-step demagnetization, you go into 2-step demagnetization, where you can see a fast demagnetization followed by a slow demagnetization. So this still demagnetizes. It doesn't recover, unlike here, for example. A demagnetization and recover, but here there is a 2-step demagnetization, which is called type 1 and type 2 demagnetization. The same occurs for n equals to 125. So if I show it for a single fluence at different values of n, I can clearly see that it goes from type 1 demagnetization to type 1 plus type 2 demagnetization. And if I calculate or extract the demagnetization time, because of this type 2 component, the demagnetization time increases to picosecond, from femtosecond to picosecond. So we try to understand what actually happens here. So in case of thinner sample, let's say n equals to 4, the thickness is such that the pump beam can go down to both pump and probe beam can go down to the substrate, and it is the uniformly excited region which is probed by the sample. So it is direct excitation. The demagnetization that we detect is always directly excited. Whereas when you go to a thicker sample, here the pump beam can reach only down to here. So, but the probe beam can reach way below that because the penetration depth is much higher. And as a result, you can see that we have both direct excitation and indirect excitation. So in the direct excitation, it is primarily spin flip scattering, whereas in the indirect excitation, it is governed by diffusive spin current or the thermal current. And in order to confirm whether our model is correct, we do control experiment. So what we do is we increase so we do a pump probe spectroscopy. So instead of a simple 400 nanometer excitation, we vary the excitation wavelength. So you can see the excitation wavelength here increases from 480 to 690. And as a result, here at 480, it is still type 1 and type 2. And as we increase the wavelength of the pump beam, we go slowly transfers into purely type 1 demagnetization. So this is type 1 demagnetization, even for this sample. So basically what happens is that as we are increasing the pump wavelength, we are slowly going deeper and deeper into the sample, and we are transforming from a direct and indirect excitation to primarily a direct excitation. So we clearly can show that both the direct and indirect excitation can coexist, and they can be controlled by simple experiment like changing the pump wavelength in this system. So this paper was published in PRB in 2018. Here, control coexcitation of direct and indirect ultrafast demagnetization in cobalt palladium multilayer. So the next one I want to study is basically the Heuster alloy system. These are magnetic intermetallics with face-centered cubic crystal, and they have composition of XYZ and X2YZ. And you can see that they have L21 structure where it's an interpenetrating lattice where both X, Y, and Z atoms are sitting on their place perfectly. And then there is a B2 structure where Y and Z can intermix, and A2 structure where all atoms can intermix. So although the crystal structure is perfect, the chemical ordering going from a disordered state, from a perfectly ordered state to complete disordered state. Okay, and they follow this latter Pauling type of behavior. So we have worked on the structure property correlation in Heuster alloy in these two papers published in 2016 and 17, where we have shown that the anisotropy damping and ultrafast demagnetization in cobalt, iron, manganese, silicon with 0.4, 0.6 composition in both cases can give rise to all these properties, and there is a structure property correlation. Question is, what if we change the composition, and can we actually see that the effect of Fermi level tuning in this case? So yes, this is the band structure of the CMS, pure CMS, and this is the band structure of cobalt iron silicon. This is cobalt manganese silicon. Here you can see the Fermi level is close to the valence band. Here the Fermi level is close to the conduction band. So if we change the composition like X and 1 minus X and vary X, then this Fermi level will be tuned from close to the valence band to the conduction band like that. And in that case, the spin density of state at the Fermi level as well as the spin polarization will change, and whether that will cause a change in the ultrafast demagnetization and damping. So we prepared this sample with varying thickness from 0 to 1, varying composition from 0 to 1. And the strict line in the read pattern clearly shows that they have a good crystal structure and a L21 phase. And from the crystallographic study also, we see that there is B2 phase as well as the L21 phase in this system. Their magnetization follows the Slater-Pauling behavior. And here is the ultrafast demagnetization result. It clearly shows that there is a non-monotonic variation in the demagnetization time. And you can see that demagnetization time increases and becomes maximum at 0.4 and then rapidly decreases. With fluence, it doesn't change much. But what about the damping? This is the Gilbert damping, and you can see this is the damped precessional motion. We modeled it with this equation, and from here we use all these complex expression to find out the damping, and this is the damping as a function of frequency, and you can see, and for different composition. And we can see damping also does not follow a monotonic behavior, but it's non-monotonic. So when we plot alpha or damping and demagnetization as a function of composition, we clearly see that they are have a mirror symmetry. So damping increases and demagnetization increases and decreases, whereas the damping decreases and then increases with composition. And at 0.4, demag is maximum and damping is minimum. This is because here the spin density of state becomes minimum. As a result, the spin flip scattering probability ASF that becomes minimum, and the ultrafast demagnetization time becomes maximum, and that causes magnetic Gilbert damping constant to be minimum. So you can see that the tau m and inverse of alpha, they are correlated. So tau m is inversely proportional to alpha, which means that damping is dominated by interband scattering contribution, and that is also sort of confirmed from these expressions for demagnetization damping, where the density of state falls in the denominator for demagnetization and in the numerator for the damping. So we understand that, and we publish this paper here. So next, I want to start, describe the spin orbit effect in spintronics. They have a spin orbit effect is a relativistic interaction between electron spin and orbital motion. It has a symmetry independent part as well as a symmetry dependent part. The symmetry dependent part are found generally in systems that lacks inversion symmetry, and they can give rise to different phenomena like PMA, the spin Hall effect, inverse spin Hall effect, spin pumping, Zalesinski-Moria interaction, and so on. So the pure spin current generation and spin to charge conversion is at the center of contention here. And this is pure spin current. So if you have spins with two opposite polarity flowing in opposite direction, then there is no net flow of charge current. So the charge current is given by this, where V up and V down in opposite direction will cancel each other. Whereas the spin current is given by this expression, where V up minus V down with spins flowing in opposite direction will add up and will give rise to a net flow of spin current. So pure spin current has negligible dissipation, unlike charge current or spin polarized current, and it has high energy efficiency for memory devices. So for that, we need a spin battery or source of pure spin current, and spin Hall effect and spin pumping effect are two effects for that. A spin Hall effect depends on the intrinsic effect of the Berry curvature as well as the impurity scattering, like skew scattering and side jump mechanism. And theta SH actually gives rise to the spin to charge conversion efficiency between spin current and charge current, whereas spin pumping effect is different. Here, if you have a ferromagnet and adjacent to it you have a non-magnet, then the precessing spin causes a spin angular momentum gradient and causes a spin accumulation at the interface of spin ferromagnet and non-magnet. And due to the difference in spin chemical potential, they can of up and down spin, they will flow into the non-magnet, and there will be a net flow of spin current into the non-magnet, which will be dissipated in the non-magnet, and the damping increases because the spin angular momentum is lost from the ferromagnetic layer. So from the modulation of damping, you can actually measure the pure spin current flow into the non-magnet and various other property. So we developed a system for novel all optical modulation method to unambiguous detection of spin Hall angle, where we have used the modulation of damping due to spin Hall torque, spin torque. So here we have taken a ferromagnet, and adjacent to it we have deposited a heavy metal. Here it is cobalt and platinum, and we flow and using two electrodes we flow the charge current to the platinum layer, and because of the spin Hall effect, spin current will be injected into the in the ferromagnetic layer, and we induces the precessional motion in here, and this spin current gives rise to a spin torque, which is given by this Landau-Lifshitz-Gilbert-Slonczewski's equation. And here, this is the anti-damping like torque, which will act collinearly with the damping like that. So it will either increase or decrease the damping. And as a result, the damping will either increase or decrease. And from here, the modulation of damping will be able to find out the Js over Jc, that is the spin Hall effect, the spin Hall angle. So we did that experiment here by measuring the damping and by varying the charge current density, the magnitude and the direction of that. And here, this is the result where you can see alpha as a function of charge current, which shows an asymmetric variation, and its value also changes, or slope changes with this angle theta. And from here, we can find out the modulation of damping, which is found out to be plus minus 7% for cobalt platinum, or sorry, it's permalloy platinum, and spin Hall angle is found out to be 0.11 or 11% spin to charge conversion. So next is the sort of the spin pumping, where we can write down the Landau-Lifshitz-Gilbert equation like that, and here the extra term, that is the spin current term, has both the spin pumping term and the backflow term. And we can write down by using this ballistic model the modulation of damping as a function of both the ferromagnetic layer thickness and the non-magnetic layer thickness, where lambda is the spin diffusion length. And we can find out the effective spin mixing conductance from here, and intrinsic spin mixing conductance, as well as the spin transparency. The spin transparency actually governs the amount of spin current transport from the non-magnetic layer, ferromagnetic layer to the non-magnetic layer. So we did this experiment on cobalt iron boron tantalum system, which were grown in our lab by using sputtering unit, and we confirmed the beta tantalum phase in this sample. We measured the sheet resistance from where we found out the tantalum and cobalt iron boron resistivity. And this is the time resolved experiment, and you can see the damping as a function of different values of ferromagnetic layer thickness. So we plotted alpha as a function of 1 over d, because you can see here that alpha changes as 1 over d, and from here we can find out all these parameters. So we did, from here we are able to find out the effective spin mixing conductance, because it shows a pure linear dependence with 1 over d, which is 6.92 times 10 to the 14 per centimeter square. And this is the non-magnetic layer thickness dependence. And here you can see the variation delta alpha as a function of t, which shows this kind of variation, which increases and then saturates. And from here, we are able to find out the spin diffusion length in tantalum to be 2.44 nanometer, and the spin transparency to be 0.5, or 50% of spin current will be transported to the non-magnet. Now, there can be two different factors which can affect the spin pumping. One is spin memory loss, where loss of spin information causes due to the spin flip scattering at the interface itself, and interfacial spin transparency, which depends on the degree of electronic band matching. There can also be two magnon scattering in this system. So we can model it by using an expression with all these terms, or we can also do a control experiment where we try to decouple the interface and try to get rid of the two magnon scattering as well as the spin memory loss. So we did that. We introduced a copper spacer layer between cobalt iron boron and tantalum to decouple the two layers. And in this case, we increased the copper layer thickness. In principle, if the two magnon scattering and the spin memory loss were to be present, then we would see a variation in the damping as we increase the copper layer thickness. But here we see that the damping doesn't vary with the copper layer thickness, which sort of proves that spin memory loss and two magnon scattering has negligible or insignificant contribution. So this attracted quite a bit of media attention, Nature India and Deccan Herald. So next, I would very quickly show you the 2D material ferromagnet spintronics. It is important because graphene is important because of its slow spin relaxation time due to low intrinsic spin orbit coupling, but it can show extrinsic spin orbit coupling because of defects in the system, which can also be varied by gate and other control. So we grew graphene, we actually procured graphene from Graphenia, and we grew cobalt iron boron layer on graphene and at this kind of pressures and all. And we characterize the interfacial roughness using X-ray reflectivity and atomic force microscopy and so on. And it shows that the values are fairly low, that is, the interface is quite good. The Raman experiment shows that they are purely single layer graphene with a defect peak, which actually shows that the defect density increases with the increase in the cobalt iron boron layer thickness. So there would be an effect of that, and we'll try to study it. So we first study the ultrafast demagnetization in pure cobalt iron boron and graphene cobalt iron boron, and these are the data and these are the fit using this expression. And here the plot, which shows that for pure cobalt iron boron, the demagnetization time is high and it does not vary with d, whereas for graphene cobalt iron boron, there is a stark change. So it actually reduces from 240 to 80, that is a factor of 3. So what is the reason behind it? In order to understand that, we also studied its the damping, because from the damping, modulation of damping, we can find out the spin pumping or the spin transport effect. And we want to see whether the spin transport has an effect on this demagnetization. So we did that. So this is for cobalt iron boron, and this is graphene cobalt iron boron. For this, the damping doesn't vary with the coffee bean thickness, whereas in this case, it varies almost linearly with coffee bean thickness. So we did the modeling using spin pumping and 2 Magnon scattering, and we found that the spin pumping has a dominant effect on this. And then we try to understand it in terms of different models. So there are 2 different mechanisms involved in ultrafast demagnetization in a thin film heterostructure. One is spin flip scattering, other is spin current transport. And in 2005, Koopmans gave a theory which shows that there can be an inverse correlation between them because of the spin flip scattering, but that was an oversimplified approach. Then in 2010, another model comes with interband and intraband spin flip scattering, electron hole pair generation and scattering. But that also gives rise to 2 different dependence, like direct correlation due to intraband scattering and inverse correlation due to the interband scattering, but that ignores the spin transport mechanism. So more recently in 2019, Zhang et al. Gave rise to another model by incorporating the spin transport model, which shows that this inverse correlation is actually due to the spin transport, where they have a dependence like that, whereas the direct correlation corresponds to the spin flip scattering. So in our case, we found an inverse correlation, and we did the modeling using Zhang's model, where delta 1 over tau m is proportional to delta alpha. And from here, we are able to find out mu s, or the spin chemical potential at the interface, and which is found out to be 0.56, which is found to be similar to the spin splitting of transition metal. So graphene turns out to be a very good spin sink material in this case. So we did a further experiment on synthetic antiferromagnet, which was published in this paper, where we show that spin transport and spin flip scattering processes can be controlled in such system by magnetic configuration. So I would actually can talk a little bit about the interfacial Zalesinski-Morier interaction. It's an asymmetric exchange interaction of this form, unlike Heisenberg exchange, which is Dij Si cross Sj. So it gives rise to chiral spin texture like that, and also skyrmions and other things. We actually measured this interfacial Zalesinski-Morier interaction by using Brillouin light scattering, which is an inelastic light scattering mechanism, where we measured the Stokes and anti-Stokes lines, and in the backward volume, in the magnetostatic surface wave geometry, we find there is a asymmetry in the spin wave frequency, line width, and so on, from where we can find out the Zalesinski-Morier interaction. So here we actually show Zalesinski-Morier interaction in cobalt iron boron and tantalum system. Tantalum is a heavy metal, as we have already shown, and we varied both the tantalum layer thickness and cobalt iron boron layer thickness. And we find out from the Brillouin light scattering experiment that there is a clear asymmetry in the spin wave, and we actually modeled it, the delta F, that is the variation in frequency for K plus and K minus, that is spin wave propagating in two counter propagating direction. And you can see this delta F as a function of K is linear, and from here we can find out the value of D, or the Zalesinski-Morier interaction constant, to be 0.22 millijoule per meter square, which is reasonably high value. And we have also done an experiment by varying the angle between the bias field and K. There's a wave vector, and from here also we can get this sinusoidal variation, and by using this expression where you can see the sin phi occurs, we are able to find out the value of D in the system. We further see that as a function of the tantalum thickness, it actually increases and then saturates at a higher value of tantalum thickness. Of course, we have done experiment on graphene, but I'm just skipping this for sake of time, because I have one last work that I want to show, which is the voltage control magnetic anisotropy. So that occurs at the interface between ultra thin ferromagnet and insulator, and due to relative charges of electron occupation in the 3D orbital of ferromagnet via the spin orbit coupling. So here you can see the ferromagnet and oxide interface, which has this ferromagnet has this 3D jet square band, and this oxygen has this 2pz band, and they actually hybridize, and there is a charge transfer between this 3D jet square to 2pz, and that introduces a sizable perpendicular magnetic anisotropy through spin orbit coupling. Now, if you apply an electric field, this electron occupation in these two bands will change, and as a result, it will change anisotropy. So there will be an electric field control or a voltage control anisotropy in this system, and which is characterized by this coefficient beta, which is the VCMA coefficient. So this is known, and we have done various experiments on that. But here we want to develop a new kind of system, that is a voltage control magnetic nanochannel or voltage control magnonic crystal in this system by patterning these electrodes. So what we did is, first we have a continuous electrode, and we have this cobalt iron boron and MgO heterostructure, and there is an aluminum oxide structure, and by using these two gates, we apply electric fields. So you can see the electric field lines shown by this down arrow that modulates the interface, and that gives rise to the VCMA. So we measure the spin waves for this uniform mode of spin wave, and we can see there is a single mode whose value shifts, so as a function of this voltage, because of the change in the magnetic anisotropy, and spin wave frequency depends on the anisotropy, therefore it changes. So from here we characterize various things like VCMA constant and so on, and then we develop this system where you can see that we have patterned the aluminum oxide, this ITO electrodes on the system like stripes. So these are the electrodes, and we connected these stripe electrodes with the bottom electrode, and now the electric field will not be everywhere, but it will
Professor
be
Burman, 1 minute more.
Yeah, actually there should be three minutes, because it's 37 minutes in my 2-3 minutes. Yeah. So
Okay.
So so I'll be finishing. Yeah. So you can see that the electric field, actually goes down only in the region where you have the electrodes. Okay. So there will be a pattern electric field in this system. So the voltage control anisotropy will work only where the electric fields are present, whereas where it is not present, it will not work. So it will cause a patterned, anisotropy in this system. And when we do that and we measure the spin wave, we can clearly see that there are two different modes in the system instead of a single mode. And when we plot their frequency as a function of the wave vector, we see that there is a clear band of valence band and conduction band kind of system, and there is a band gap. So this electric field control switchable, anisotropy opened up a magnonic band structure and band gap in the system, which is very unusual and very interesting. And we did this numerical simulation by plane wave method, and we can see that the mode 1 actually flows through the region 1, whereas mode 2 flows through region 2, and they also have adjacent to each other, so they can repel each other. So there is a mode anti-crossing in the system, which gives rise to this band gap. And when we apply a reverse field like 4 volt plus 4 volt, the band structure changes and the band gap also changes. And here the mode also switches from region 1 to region 2. So yeah, and we did the reconfigurability experiment here by applying different voltages, or zero voltage, or not patterned, unpatterned substrate, and so on. So this also, was published in Science Advances recently in 2020, and this also attracted quite a bit of media attention. And with that, I will finish. So I have, explained to you the different mechanisms of ultrafast demagnetization from spin transport and spin flip scattering process. I have shown you the spin Hall effect and spin pumping effect measurement by using all optical effect. I have shown you the 2D material ferromagnet spintronics, and I have also shown you the interfacial Zalesinski-Moria interaction, as well as a voltage control magnetic anisotropy based magnonics in this. So this was my research group, and you can see it's quite a big group, and you can probably recognize this person, Professor Joybardhan Sinha, who is now at SRMIST and doing quite well there. He had contributed quite a bit in our research work there. And these are my collaborators from different parts of the world. And these are the two books. And you can see in this book, Professor Joybardhan Sinha is also a co-author. So this book is a very good source of understanding of spin dynamics and related phenomena. And with that, I will thank you all. And I will advertise a little bit on different review article and perspective that I have written during the lockdown and afterwards. And here is the list. Thank you very much.
Okay, thank you, Professor Anjan Barman, for your nice presentation. Now it is open for the audience for questions. Due to the time constraints, we will take 1 or 2 questions. So here is one question. Professor Barman, can you see this question?
Yeah, I can see John Donald Raj.
Yeah.
So I said in Hysterala system, as the composition of changes, the Fermi level shifts. However, the band gap remains the same irrespective of the composition. What is the application significance of the Fermi level shift in the half metallic material? So yeah, as the Fermi level shifts, overall bands, although the band gap remains the same, but the spin polarization changes. And as a result, as the spin polarization changes, that causes a change in the spin transport in this system. And you can see that the density of state at the Fermi level also changes, and that causes a change in the ultrafast demagnetization and the damping in the system. Okay, so the next question is from S. Ratha, and so what is the size of the ITO top electrode? It was about 220 nanometer, and it was done by the electron beam lithography. Then the next question is, why did you deposit SiO2 on top of the sample? Yeah, in some sample, for example, for the Zalesinski-Moria interaction sample, cobalt iron boron, tantalum, cobalt iron boron, and then we deposit SiO2 in order to break the inversion symmetry. Okay, so that on 2 different surfaces you have 2 different material, and that breaks the inversion symmetry in the system. Yes, so I have answered
Okay,
fairly to this question.
okay. So thank you very much. Actually, due to the time constraint, we cannot continue further. So thank you, Professor Anjan Burman, again for your nice presentation. And thank you very much, the organization committee, for giving me an opportunity to chair the session.
Yes.
Over to Dr. Obey.
Yes. Thank you to everybody. Thank you, Professor Tripathi, for chairing this session. So now we declare that this session is over and the other parallel sessions will be starting soon. Thank you.
Thank you.
Thank you very much.